All right, I also wanted to walk through one of these rational root type problems, specifically geared towards a calculator. Now, when we have a calculator, the reason we tend to have that at our disposal is when the rational root theorem is usable but just simply too complicated, right? Negative 192 has a ton of roots. So if we had to guess and check at possible rational roots, we would be here for quite a while, right? It's just a matter of efficiency. So rather than going through that whole process, the calculator problems allow us to basically fast forward to a solution or possibly two solutions that work for us. So using your graphing calculator or a program like Desmos, you can certainly go ahead and graph this polynomial. And when I did, I ended up with a graph that looks like this. You can see these graphs get pretty unwieldy. You can see my vertical scale goes down to negative 400. But the important things, what we're looking for here, are x-intercepts. And so what I'm going to do is I'm going to write down both of them. I know that negative 6 is a solution and 2 is a solution. Not only do I know that those two solutions, those are two solutions to my problem, but I also know that when I synthetically divide my original problem using one of those roots, I will get a remainder of 0. So this is, like I said, a shortcut that allows us to cut out all the guessing that we did on a non-calculator problem. So again, once we have one of those roots, these problems look very similar. I'm going to synthetically divide. So the 1 comes down, I multiply by 2, I add, I multiply, I add, I multiply, I add, and again, I multiply and get 192. Again, we're very happy when we get 0 as a remainder. It's also a good way to check to make sure that your graphing made sense, right? If you didn't get a remainder of 0 here, something has gone wrong. So now that I have my synthetic division, I can rewrite my polynomial, right? This ugly 5-term quartic polynomial, I can rewrite as the product of a linear x minus 2. That 2 leads to the factor of x minus 2. And then the result of my synthetic division gives me the remaining part of my polynomial. X cubed plus 6x squared plus 16x plus 96 all equals 0. So we've cut our polynomial down to size. We now have, instead of a quartic, a linear times a cubic. And I believe this one will factor nice and easily by grouping. X squared comes out. I'm left with x plus 6. Over here on the right, 16 will come out. And again, I'm left with x plus 6. That's what I'm looking for. So my final factor form here will look like x minus 2 times x squared plus 16 times x plus 6 all equals 0. Now I'm going to solve each of those factors independently. Let's just pretend that this isn't here so it doesn't mess us up. So I know my first solution is going to be x equals 2. I knew that from the graph, but I can also verify that in factored form. I know that when I have x plus 6 as my factor, my solution will be negative 6. And then for this problem, it's probably worth it to write it out and go through the process. Remember, we're setting each of these factors equal to 0. That leads us to just flip the signs when things are simple. But when things are more complicated, we may have to just slow ourselves down and go through the whole process. Subtract 16, and then we take the square root and get plus or minus 4i. So there's two solutions, positive 4i, negative 4i, and then negative 6 and positive 2 represent my two real solutions. So when we have a calculator problem in these solving polynomials, we want to graph the whole polynomial and really focus on finding x-intercepts. Those are our real roots. Those are legitimate answers to our problem. but more importantly, they allow us to synthetically divide our original polynomial and turn that messy quartic into the product of a linear and a cubic polynomial. And that opens up more options for us. Once we have this cubic, we can then try and factor by grouping. Once we factor, we set each factor equal to 0 and solve. And that's it. Thanks, guys.